Hello, team. Hello. We are going to look specifically at half-lives in this particular video because we've been looking at kinetics, right? We did zero order, first order, second order kinetics. So instead of doing the half-life in each one of those videos and doing it 3 times, I just thought, let's just throw it all together. Still debating whether I wanted to go into some details on some of the cool nuclear chemistry that comes with that. We'll see how long the video takes, but my main focus right now, obviously, is to define what half-life is. You've probably heard of it, right? I think everybody's heard of carbon-14 dating and stuff like that. It's kind of really neat, but you can do carbon-14 dating. You might do that in some, like a geology class or something, and they'll just give you the equation. But if you understand kinetics, you'll go, oh, I've seen that. That's a first-order reaction integrated rate equation, just modified a little bit. So if I have some time at the end, I'll kind of show you what they do. Insert this, substitute this in, and you can see where this carbon-14 dating equation comes from, derived from first-order kinetics plus half-life. So it's kind of neat. But I think let's just define half-life, kind of look at, can we use that as a tool to determine reaction order? Because remember, the first thing we always want to do when we have a problem in kinetics, what's the order of the reaction? And I've showed you how to do that with plots, plotting certain ways to, certain forms of the concentration versus time to see if you get a straight line. We looked at units on the rate constant, right? Those are some tricks. But we can also use the half-life. So if we have concentration versus time data, we can kind of look and see, hey, what's happening with the half-life here? And we can kind of get a good guess on the order of the reaction from that half-life data. And also, I want to derive equations for zero order, first order, and second order reactions relating the half-life to the rate constants and the initial concentration. So again, defined should be kind of, it's in the name, right? Half-life, how long does it take for the reactant to drop in half, to go to 50% of what it was? So if you had 10 grams, how long does it take to go to 5 grams, right? And then how long would it take to go from 5 grams to 2.5 grams, et cetera, et cetera, et cetera. So you can keep going half, 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 half. How long does it take each time? We're interested in, well, is that constant? Is it dependent on the initial concentration? Does it speed up? Does it slow down? Those are some questions chemists like to answer, right? So that's just the definition. How long does it take for the reactant to go from its initial concentration to half of its initial concentration? That's kind of a useful little thing. And again, great for radiocarbon dating. Right, because remember, first-order reactions, radioactive decay are first-order processes, so it works out kind of nice. Hopefully you have your notes with that equation for the first-order integrated rate equation. So what we're going to do is we're going to do some algebraic substitution. We're going to take the zero, and if you want to jump ahead and see if you can derive these equations before I do, I'll show you what you're going to do, and you can pause the video and see if you can just pencil it out. If you got nothing better to do today or right now, right? Or if you're on a boring date or something, excuse me, you're so boring, it would be much more exciting to derive half-life equations from integrated rate equations. You'll never see them again, I guarantee you. All right. So what we're going to do, we're going to take the integrated rate equation and say, well, when t, the amount of time elapsed, is t half, the half-life, right? Well, then the concentration at time t should be 1/2 of the initial concentration. So A sub t would be 1/2 A naught. So what you do is you take the integrated rate equation. Instead of writing t, write t sub 1/2, right? So we're defining that as the half-life time. And wherever you see A sub t, that final concentration, and that's in zero, first, and second order, well, instead of writing that, put 1/2 the initial, A sub naught, or A sub 0. And you'll see that the A sub naught terms can be combined, canceled out in certain ways. And just do your algebra, see what you get, right? And it'll take you a few minutes, but see if you get what I got. And we'll do it again. We'll do zero order, first order, and then second order. And then, and that's just what we're going to do. Substitute those into the integrated rate equation, and we'll derive equations. I will provide you these equations in my class if you need them. But it's good to know how to derive equations from other equations through algebraic manipulation and algebraic substitution. It's a great skill to have. So these equations that relate the half-life to the rate constant, because that's from the integrated rate equation, and the initial concentration, that'll be very useful for us, again, to predict reaction order, possibly, and to calculate, kind of a shortcut, how much of a substance is left after a certain amount of time. If you're dealing with half-lives, or specifically if you take nuclear chemistry or geology or something and you do radiocarbon dating, or maybe dating of rocks, and I'll talk about why carbon-14 can't be used to date billion-year-old rocks. We have to use a different isotope to do that. So let's go ahead and do these derivations real quick. And we'll talk about it. We'll talk a little bit about radiocarbon dating, and then do an example problem and show you how we can calculate rate constants. That's a key, right? If you're given half-lives, you can actually calculate rate constants if you know the reaction orders and stuff. Woohoo! Let's do it. Hopefully you did it. All right, let's see if you match what I got. And hopefully I did it right? Sometimes you miss a negative sign or something. That can mean all the difference in the world, that dumb negative sign, right? Hits you in thermodynamics. All right, so let's do zeroth order reactions. We'll do the exact same thing for first order and second order, so you can jump ahead of me. So just write the integrated rate equation, right? For zero order reactions, the concentration at time t is just equal to negative AKT plus the concentration initially, right? And typically, especially for first order, A is typically going to be 1. So most of the time you're going to see, especially if you look at radiocarbon dating, isotopic dating, in anything related to that, in a non-chemistry environment, you're not going to see the little constant A, which is the stoichiometric coefficient from the balanced equation, because it's almost always 1. All right, no big deal. So if you don't see the A, don't freak out and go, it's just 1. Okay, no big deal. Now what we're going to do is do that algebraic substitution. We're going to let T equal T1/2, the half-life, and at that point, the concentration at time t will be 1/2 the initial. So I'm going to look at my equation and go, one concentration at time t will now be 1/2 the initial concentration. By definition of half-life, will be negative AK. Now t becomes t to the sub 1/2 plus the initial. So that concentration at time t, that variable's gone. Now we've got two initial concentration terms. We want to combine those. So what I did, I want to get t to the 1/2 on the left-hand side. So I just moved things around. I just flipped equations and whatnot, right? So I just moved things around. So I took the negative AKT to the 1/2 and put it over on the left-hand side, and the 1/2 A naught on the right-hand side. And then I want to get A naught initial over this side. So I'm going to take 1/2 A naught, and I'm going to subtract the initial concentration from both sides. So that's where you get the 1/2 A naught minus the A naught. I just moved it to the other side, leaving everything else the same, and just flipping the left side with the right side, because sooner or later I want to get the T1/2 on the left. You can do that sooner or later, doesn't matter. All right, now I can couple these terms. So 1/2 A naught minus 1 A naught will be negative 1/2 A naught, right? Okay, just combining those terms, that's nice. So negative AK T to the 1/2 will be negative 1/2 A naught. Well, the negative signs should cancel out. All right, you can't have a negative half-life or a negative rate constant, right? So let's isolate T to the 1/2. So I'm going to divide both sides by A and K. And again, if A is 1, it just drops out of the equation. So T to the 1/2 will be the initial concentration in the numerator, that number 2 in the denominator, the stoichiometric coefficient in the denominator, commonly 1, and the rate constant in the denominator. So here's the equation we're after for zero-order reactions. The half-life is the initial concentration over 2AK, A commonly being 1. So commonly you'll see it without that in there. So now if you know the half-life and the initial concentration, you can calculate the rate constant. Or if you know this and that, you can calculate that. You've got those three variables that are in there. But the main thing I want you to look at in order to determine reaction order is that T1/2 and the concentration initially are proportional. They're directly proportional. So as a reaction progresses and the initial concentration's going down, remember the graphs, it's dropping, because the reactant's going away, so it's going down, going down. Okay, sorry. So as that goes down, the half-life will also go down. So what that means, as a reaction's progressing, the half-life is decreasing, which means it's kind of speeding up a little bit. Oh, interesting, right? So what I want you to remember, and I'll give you this equation, but I want you to look at that and go, okay, half-life and initial concentration are directly proportional. So if you look at concentration time data for a reaction and you don't know the reaction order, if you've got a data table or a graph, you can kind of eyeball it and go, oh, look at that. When the concentration drops in half, it took this amount of time. And then from that point, it drops in, so like 10 grams to 5 grams. How long did it take? Then 5 grams to 2.5 grams. How long did that take? Well, if it's the same number, it ain't zero order. Got to love my English there. But if that half-life decreased, say it went from 15 seconds to 8 seconds, or 7.5 seconds, or whatever it is, that half-life is decreasing along with it. You go, oh, that's a zero-order reaction. That's how those function. Not too bad. So see if you can do this for the first-order reactions. Write down the integrated rate equation. Substitute in 1/2 A naught for AT and T 1/2 for T. Isolate T to the 1/2 on the left-hand side. See what you get, and then tell me whether the half-life is proportional to, inversely proportional to, you'll see concentration at the bottom, or independent of the initial concentration. Those are the only three options, right? See what you get. I'll do it myself as well. How'd you do on this one? All right, let's do first order reactions, and we'll do second order reactions next. So here's the integrated rate equation. I took the one where both AT and A naught are in the log term. So log of AT over A naught is negative AKT, right? And if you want to put A equals 1 in there, that's perfectly fine. Let T equals T 1/2. Let the concentration at time T be 1/2 the initial concentration. Substitute them in. Algebraic substitution. Know it. All right, so AT becomes 1/2 A naught over A naught equals negative AKT to the 1/2. Well, wait a minute. Whoa. The initial concentration just canceled out. Whoa, that didn't happen in the zero order, did it? Ooh, that just went bye-bye. So now we just end up with log of 1/2 is equal to negative AKT to the 1/2. And if you put in 0.5 into your calculator, do the natural log, you get 0.693, something, 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 something. Every textbook I've ever seen just truncates that to 0.693. It's actually 0.693, I think like 1.4, blah, 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 blah. So three significant digits apparently is the universally accepted number for every textbook I've ever seen in my entire life. All right, rock and roll. So log of 1/2 is negative 0.693, right? It's a number smaller than 1. You take a log of another number smaller than 1, it's a negative, right? It's negative AKT to the 1/2. Well, look, the negative signs cancel out. So I'm going to isolate T to the 1/2 to the left-hand side. So let's take 0.693 divided by A divided by K to isolate T to the 1/2 and just flip the left and right side. So there's your half-life equation for first-order reactions. Half-life is 0.693. Good to 3 sig figs there. Divided by A, which is commonly 1, divided by the rate constant. Rarely do you see rate constants with more than 3 sig figs anyway, so I can understand why 0.693 is fine. Well, you'll commonly see it this way, but there's no concentration term in there. Wait a minute. Zero order reactions, the concentration term, initial concentration, was in the numerator, so the half-life and the initial concentration were proportional, but it's not in there. So which means as a reaction, as a first order reaction is progressing and the initial concentration, A naught's decreasing, it has no effect on the half-life. It's independent of the initial concentration, which means the half-life is constant. That is a hallmark red flag for first-order reactions because zero order and second order do not do that. So if you look at concentration versus time data and you don't know what the reaction order is, and you can say, okay, the time it takes to go from, say, 20 grams to 10 grams is 5 seconds. And then, or 20 to 10, say 20 grams to 10 grams was 5 seconds. And then 10 grams to 5 grams was also exactly the same amount of time. And then from 5 to 2.5 was exactly the same amount of time. So if that half-life is constant, every time that concentration drops in half, you know right there, boom, first order reaction. So we'll look at some tables for that. Maybe I'll do that next. I'll draw up a little kind of a fictitious table so you can kind of eyeball it from a graph real quick. You can see it in the data table, you can see it from a graph, but I'll just kind of show you real quick. We'll just take a few seconds and look at it. Let's say you've got some concentration versus time. We looked at this in one of the first videos we did on kinetics. You can see that reactant is dropping over time, and we want equations to represent that. But we don't know the reaction order. Let's real quick, we can eyeball it and do the half-life and see if we can see if the half-life decreases as A naught increases, those kinds of things. We can look and see if it's independent. Most of the time, we're just going to look at this and look for constancy in the half-life, because that tells you it's first order. Typically, we won't do it for second order. We'll just take a quick glance and look, hey, is this a first order? Because you can do it in a few seconds. So let's take a look here. Let's say we start at 400. That would be the initial concentration. Well, half of that would be to like 400. Molar's probably not the best unit for this. But hey, whatever. It doesn't matter what the units are, right? Actually, let's get rid of the units. So this could be minutes, seconds, hours. I'm like, 400 molar, holy moly, isn't water like 55.5 molar? I don't know, anything like that. So we'll just say whatever units there are on the concentration. but we go from 400 of whatever that is to 200. Well, that would be dropping in half, right? Well, how long did that take? Well, let's look across here. So we're coming down between about halfway between 10 and 20. So that looks to be about 15 seconds right here. Or 15. Yeah, we'll go ahead and make that seconds just to put a unit on there. All right. So in this situation, it took 15 seconds to drop in half from its initial concentration. Well, now let's start here. Starting at 200, dropping in half would go to 100, which would be right here. All right, let's look down. So we're dropping to 100. From 15 to 30 is 15 seconds. So that's T1/2. Oh, wait a minute here. Do you see that? It took 15 seconds to go from 400 to 200 and 15 seconds to go 200 to 100. Well, let's take a look. That's good enough right there. You can see it's constant. Well, then 100 to 50 is right about there. 30, 40, 45. So that's also about 15 seconds. So in this scenario, you can see that the half-life is constant. So in this case, T1/2 is constant. We can just see it. You don't even have to write that. You can just eyeball it from the graph. Therefore, that must be a first order reaction. So that's another way, besides units on rate constants and doing plots. In this case, first order would be the natural log. If we plotted the natural log of the concentration versus time, boom, we'd get a straight line, wouldn't we? So we got 3 ways to determine reaction order now. Ho, ho, ho. And again, this is how most decomposition and all radioactive decay concentration time moves. You see that function, the way it works its way down. We want to put an equation to that, which we just did. Let's do it for second order. So take the integrated rate equation for second order reactions, plug in T1/2 for T, 1/2 A0 for AT, see what you get. Test yourselves! How'd you do on this one? All right, so here's our second order integrated rate equation. So remember, it's the inverse of the concentration at time T is AKT plus the inverse of the initial concentration. So again, just like we did 0 in first order, let T equals T1/2, substitute that in. Let A sub T equal 1/2 A sub naught, substitute that in, and let's isolate T to the 1/2. All right, so instead of A sub T, I'm going to put 1/2 of A naught. That will equal AK T to the 1/2 plus 1 over A naught. A sub T is out. I want to combine those A naught terms, and I want to get T to the 1/2 on that side. So I'm going to flip sides. So I'll put the AK T to the 1/2 on this side. And instead of 1 over 1/2 A naught, I'm just going to write that as 2 over, right? Flip the 2. So 1 divided by half is 2, right? So that I just, oh, see that spit just go, blah, blah, blah. Splat, sorry. So we get 2 over A naught. Well, I want to get that over to the other side. So I'm going to subtract 1 over A naught from both sides. So AKT to the 1/2 will be 2 over A naught minus 1 over A naught. Well, 2 minus 1 is 1, so we get 1 over A naught. Right? There's no negative signs. Like the other ones, we had negative signs canceling out. There's no negative signs on this one. So AK T to the 1/2 equals 1 over A naught. Let's isolate T to the 1/2. So I got to divide both sides by A, divide both sides by K. So I'm going to get 1 over A, K, initial concentration. So it's not independent like first order. First order is the lucky one. It's independent of the concentration and easy to spot on a graph like we did last time, a plot. But this is different. 0 first order are all different. Remember, as 0 order reaction, A naught was in the numerator, so it was proportional, directly proportional to the half-life. I mean, to the half-life. So as the concentration decreases over time, the half-life decreases. First order, it was independent, so half-life's constant. But this one, since the initial concentration is in the denominator, as that decreases over time, wait a minute, so I'm going to be dividing by a smaller number. That means the half-life's going to go up. Wait a minute, so as A naught drops, T1/2 gets longer, and it's going to take longer and longer for this reaction to progress, right? So these are inversely proportional. So a great way to check for reaction orders, other than units on the rate constant or making plots and plotting either the concentration, log of the concentration, or inverse concentration versus time, looking for a straight line, you can look at half-life and initial concentration dependency from graphs and data tables and go, wait a minute, if they're directly proportional, it's zero order. If they're independent, right, if T1 half is constant, that's first order. But if they're inversely proportional, that would be second order. Hey, okay, so we got a few minutes. Maybe I'll talk a little, we'll do an example. I want to do an example of how to calculate rate constants given half-lives, or vice versa. Given a rate constant, you can calculate the half-life. Pretty easy to do. We'll focus just on first order because that's typically 99% of the time what you're going to be dealing with, because you don't have to worry about the initial concentration, right? And then if we have time, maybe do a little radiocarbon dating. Ooh, getting into the fun stuff. All right, you'll do this a lot in my class, but I might give you some problems where I don't want to give you the rate constant directly or the half-life directly. I'll give you one or the other and either tell you or give you a hint on if it's zero first or second reaction order, zero first or second order reaction, and then you have the half-life equation. So given a rate constant, you can calculate the half-life. Given the half-life, you can calculate the rate constant. For first order, easy. If it's zero or second, you need the initial concentration as well because it's dependent on that. So here's a typical example, and sometimes I'll give you the half-life in order to get the rate constant in order to do something else, so kind of like a part A, part B type thing. Well, let's say we've got radioactive decay, hint, hint, first order. We got carbon-14, go into products. We haven't done nuclear chemistry. Products aren't important at this point. We also know there's a coefficient of 1 there, so A is going to be 1. If the rate constant is 3.83 times 10 to the minus 12th inverse seconds, what is the half-life? Now, it's going to be a time, so let's do it in years. So see if you can do that for me. So what we want to do is recognize a couple things. In order to relate the half-life, if we're going to relate the half-life to the rate constant, we need to know what order. This is a first-order reaction. And you can determine that a couple of ways. We know it's radioactive decay. We know the units on K are inverse time, right? So units on K or decay process. Decay process squishy. So you can look at it either way. Best to go from the units on K, that's definitive. We're just assuming if it's radioactive decay or decomposition, it's going to be first order. But if you got to, like I said, if you don't got stuff and you got to make an assumption, you might have to make an assumption. But hopefully we don't. We don't like making them if we don't have to. So we know it's first order, so we can look at the half-life equation. So the half-life for a first order process, and I would provide you this, right, is 0.693 over AK. Now we know from this that A is going to be equal to 1. So there's nothing there. That means it's 1. So should be pretty easy, right? We know A, we know this, we know that constant. You should be able to solve for T1 half. That'll be in seconds, of course, and then convert that to years, right? So seconds to minutes, minutes to hours, hours to days, days to years. Now, the number of days you use in a year might give you slight variability in the maybe the last significant digit or some non-significant digits. But see what you get. Go ahead and do that. Calculate the half-life of, some of you might have this memorized, of the radioactive form of carbon they use for carbon-14 dating. So when they say carbon dating, they mean carbon-14, because carbon-12 is the main, most dominant isotope. That's stable. Same with carbon-13. So it's carbon-14, which is the one that decays away over time, right? So if you got carbon-14, it's going to go, you're going to lose half of it every, I almost told you the answer, every certain number of years. Calculate how many years it takes for half of the carbon-14 to go bye-bye after a living system, which is a living, breathing system. Plants, people, you have a certain amount of carbon-12 and a certain amount of carbon-14 in you. Once, say, a tree dies or something like that, you make a bowl out of it or whatever, the carbon-12 is set, but the carbon-14 decays at a constant rate. Ooh, do you see? We might be able to use this in our advantage and first-order reaction kinetics to calculate how many years has gone by based on the amount of carbon-14 left versus the amount of carbon-12 left, and comparing that in that bowl to a current living system, right? Oh, it's kind of interesting. Solve this for me real quick. Did you get my number? You ready? So let's take our equation for first order. Half-life is 0.693 divided by AK. So 0.693, that's good to 3 sig figs, right? Divided by 1, that's exact. divided by K, but I want to write it so I get the seconds in the numerator. So 3.83 times 10 minus 12 inverse seconds, so I flip the inverse seconds into the numerator, right? That way I can track my units and I can go, oh, okay, that's seconds, but I want it in years. So 60 seconds per minute, right? 60 minutes per hour, 24 hours per day. And I did 365.25 days. I think that accounts for leap year. But, if you did 365, 364, you're going to get the same answer regardless. So, but I did the 365.25. I think that accounts for leap year. What the hell, leap year? Okay, anyway, you'd think they could fix that by now in daylight savings time and make it all the same for everybody. So days cancels. Leaves me with years, all right? These are exact. That one doesn't matter. 3. So we're going to 3 sig days regardless. So the half-life for the carbon-14 isotope, which undergoes radioactive decay, and if you take nuclear chemistry, you'll be able to know what those products are and do the kind of cool equations. I get 5,733.6 years. Good to 3 sig figs. Round that to 5,730 years. That's typically the number you're going to see for the half-life of carbon-14, which means every 5,000, so if something that was in a living equilibrium with the atmosphere, right, because in the atmosphere, carbon-14 is created, as cosmic rays come down, I think they hit a certain isotope of nitrogen, which creates the carbon-14, which starts to immediately decay, right? Well, if you're a tree or a person or a monkey or something, well, you're absorbing that through carbon dioxide, right? So you have when you're alive, you have a certain ratio of carbon-14 atoms to carbon-12 atoms, and pretty much within experimental error, the same as the atmosphere, the same as people, whatever, right? But once that substance dies and is no longer ingesting carbon dioxide from the atmosphere, its carbon-14 to carbon-12 ratio, boom, that's the moment it was gone. So maybe a tree was cut down and they make, some object out of it. Okay, after 5,730 years, the carbon-12 will still be the same, but the carbon-14 dropped in half. Oh, right. So if you found a sample and measured its carbon-14 to carbon-12 ratio and found it was about half of what it is to a current living system, that is roughly 5,730 years old. That was made about that long ago. Neat. That's pretty good for some, ancient historical documents. Well, if it drops in half again, right? So if it does another 5,730 years, it drops again. So half. So if it's a fourth, so if you find a bowl or something or an old staff, right, and find out that that is a fourth, the carbon-14 to carbon-12 ratio is 1/4 of what a modern living system is in equilibrium with the atmosphere. That's gone through 2 half-lives, 1/2 and 1/2, so it's a fourth, right? So that means it went 2 times this, so a little over 11,000 years old. Well, there's a limit to how far you can go. I think the limit to carbon-14 dating is 50, 60,000 years before it starts becoming, uncertain for that. But you can get things up through modern human behavior up to 20, 30, 40,000 years ago. You're covering a lot of human history there. It's just a fantastic way of doing it. So I'm going to take the last minute and kind of show you this carbon-14 dating equation that's derived if you're not in chemistry, but you can see the parallel. I'll show it in parallel with the first order integrated rate equations. Hopefully you can kind of see where that comes from. I don't think we have time to do it. Maybe I'll have time to do a problem. We'll see. All right, real quick, if you're in geology or you do radiocarbon dating, you can do this for rocks too, but I think they use lead-206 and uranium-238 or something, which has like a half-life. Uranium-238 is like in the billions of years. Right? You couldn't radiocarbon date a rock that was billions of years old. It's limited to 50, 60,000 years, give or take. So if you want to do really old things like rocks, like I said, I think you can do the ratio of the uranium-238 to lead-206 or something and get a rough idea, how many billions of years old the rock is. But for radiocarbon dating, again, this is our first order reaction kinetics. Right, log of AT over A naught is negative AKT. Well, we know the rate constant from the half-life, first order, is 0.693 over AT to the 1/2. So let's substitute that in for K. And in radiocarbon dating, they'll look at the concentration time T over initial time. You'll see this N, number of carbon-14 atoms, NF over N initial, or NF is commonly the ratio of carbon-14 to carbon-12. in that object that has, is no longer living, and initial, no, I mean, and final is it's the amount of carbon-14 to carbon-12 since that object's no longer living and the carbon-14's been decaying. And then the initial would be a current living sample, right? The ratio of carbon-14 to carbon-12 in a sample in equilibrium with the environment. Commonly, that's just a percentage. So they'll say, hey, this ratio would just be a percentage of the carbon-14 left, right? So say it's 52%, just put 5.52 in there. Percent of carbon-14 left as compared to a living sample. Because remember, every 5,730 years, you're losing half your carbon-14. At that point, that tree was cut down and that staff made or something, right? So let's substitute this in, and I'll leave it as AT over A naught, but commonly you'll see NF over N initial or some form of it like that if it's a non-chemistry thing. All right, well, log of AT over A naught, I'm going to substitute this in as negative A. I'm going to substitute in 0.693 over AT to the 1/2 for the rate constant, get the rate constant out of there, times T. T is the age of the sample that we're after, right? So let's isolate that. So let's take log of AT over A naught. A cancels out, right? Boop. A goes bye-bye. Let's multiply by T to the 1/2, divide by 0.693. So the age of the sample, since it was created after, destroying some kind of system that was in equilibrium with the environment, now it no longer is, start the clock. Carbon-14 starts decaying every 5,730 years. Half of it's gone. Carbon-12 stays constant. So you're looking at the ratio of carbon-14 to carbon-12, comparing it in that artifact you found in that fossil compared to living samples. That's just the log of AT over A naught. Typically, that'll just be the percent of carbon-14 left compared to a living sample, times the half-life, which we know is 5,730 years, divided by 0.693. So we can do a quick problem with that. Take us a few seconds, and we can estimate the age of a fossil or some ancient artifact. Kind of cool. This is application. Normally, this is making this video a little longer than I wanted, but it's kind of a cool application of first-order reaction kinetics. All right, real quick, right? If you want to do a real quick carbon-14 example, let's say, we dig up some ancient artifact, say some Viking burial tomb or some Egyptian tomb. Hey, that'd be so cool. Be an archaeologist and dig something up that nobody's seen. I'm a coin collector, so it's just to be able to, can you imagine digging up a treasure trove of coins from, 900 years ago or 3,000 years ago or something like that? Did they even have coins 3,000 years ago? Probably not. But anyway, just digging that up, that history is just amazing. But like I said, if that artifact was made from a tree or some kind of living system that was cut down and then, separated from its equilibrium with the environment, we can radiocarbon date it. So let's say we do I didn't talk about how, we find out that artifact has 25% of the carbon-14 left as compared to a living sample, right? How old is the artifact? Well, we know the time elapsed since that artifact was created. How old it is equal to the log of AT over A naught, and that's the percentage, right? So you can put 0.25 in for that ratio, times the half-life, which we know is 5,730 years, divided by 0.693. Calculate that. See if you get what I get, and we can get a rough estimate how old this artifact is. Ooh. All right, did you get what I got here? So we've got our problem here. I forgot my negative sign. Can't forget the negative sign, right? Because if you forget that negative sign, you'll end up with a negative years. It's like, wait a minute, it's going backwards in time. So here's our equation. We know that 25% or 0.25 is the ratio of AT over A naught, so we'll plug in 0.25 there. Half-life is 5,730 years, 0.693, plug it in. Well, let's do that logarithm first. So log of 0.25, that's going to be negative because that's smaller than 1, right? I get negative 1.3862. 2 sig figs in the log gives you those 2 decimal places, right? 2 significant digits after the decimal point. Those negatives will cancel out, right? Plug in the 5,730 years for the half-life, 0.693. Everything's got 3 sig figs. So I punch that out. I get 11,461 years. Rounds to about 11,500 years old. So you just kind of, boom, run that in there. You can date that object. You're off to the races. Kind of cool, right? So I'm not going to give you carbon-14 dating problems in my class, but I just wanted to show you how we can transition from first-order reaction kinetics to a real-world example. Cool stuff, man!